So the previous section had a really nice discussion of lack of assumed the independence assumption in typical statistical testing in machine learning. It made me think quite a bit about a paper by Rotem Dror and some of her colleagues called Replicability Analysis for Natural Language Processing, Testing Significance with Multiple Data Sets. And what she talks about there is basically multiple comparison issues and lack of independence between data sets. So I'll put a link to that down in the description of the video. With that, where Salzberg goes from here is talking about alternative statistical tests to deal with these problems of multiple testing and also lack of independence. I'm going to skip that whole section. If you want the mathematical details, see section 3.1 of the paper. And I'm going to go to the next three parts where Salzberg talks about three big things besides the multiple testing comparison that really plague machine learning experimental design, particularly bad experimental design. So these two things are what goes wrong when lots of people are working with the same data sets. It covers over-tuning or repeated tuning, as he calls it, and over claims, or what you might think of as overly optimistic conclusions about generalizability. And all three of these are important in machine learning, in natural language processing in particular. So I'm going to go into these in some level of detail. All right, section 3.2, community experiments, cautionary notes. Here's the material that I skipped. Okay, 3.2, community experiments, cautionary notes. Community experiments, I think, is a really nice term, so keep it in mind. In fact, says Salzberg, the problem in the machine learning community is worse than stated above because many people are sharing a small repository of data sets and repeatedly using those same data sets for experiments. Thus, there is substantial danger that published results, even when using strict significance criteria and the appropriate significance tests, will be mere accidents of chance. Now, before I go too deeply into this, I want to point out two things. One is Salzberg is, while he's critiquing repeated use of shared data sets, he also is going to come back to later on what's good about shared data sets. And number two is that I personally have been a huge proponent of shared data sets. I've been involved in making a number of them, mostly through the biocreative shared tasks. I get why having shared data sets is important from a number of scientific perspectives. However, I share Salzberg's issue with reliance on using the same data sets over and over when the only point you're trying to make is my performance is the state of the art, it's better than everybody else's. That's not what shared data sets are best used for, versus trying to understand when things do and don't perform well, what the causative factors are. And that's a very different kind of thing from claiming, I'm better than everybody else. Okay, back to the beginning. In fact, the problem in the machine learning community is worse than stated above because many people are sharing a small repository of data sets and repeatedly using those same data sets for experiments. Thus, there is a substantial danger that published results, even when using strict significance criteria and the appropriate significance tests, will be mere accidents of chance. The problem is as follows. Suppose that 100 different people are studying the effects of algorithms A and B, trying to determine which one is better. A little bit of my own comments here. Obviously, I hate the framing the question as which one is better, whatever better means, versus framing your experiment as trying to learn something. Okay, end of my rant. Suppose that in fact, both have the same mean accuracy on some very large population data sets, although the algorithms vary randomly in their performance on specific data sets. Now, if 100 people are studying the effect of algorithms A and B, we would expect that 5 of them will get results that are statistically significant at the p less than or equal to 0.05 level, and 1 will get significance at the 0.01 level. A little Kevin interjection here. This is based on the idea that if you have a significance level of 0.05, you do 20 tests, you would expect by chance that one of those would give you statistically significant results without that actually meaning anything. It's just by chance, all right? Back to Salzberg. Actually, the picture is a bit more complicated since this assumes the 100 experiments are independent. A little Kevin interjection, they're not independent, right? These are all on the same data sets and probably with people just using different versions of the same algorithms with little tweaks, as we discussed in the introduction section. Back to the paper. Clearly, in this case, the results are due to chance, but if the 100 people are working separately, the ones who get significant results will publish, while the others will simply move on to other experiments. Dent in 1985 made similar observations about how the reviewing and publication process can skew results. I'll insert here that I think we're just talking about is what we would call today publication bias. Back to the paper. Although the data mining community is much broader than the classification community, it is likely that benchmark databases will emerge and that different researchers will test their mining techniques on them. The experience of the machine learning community should serve as a cautionary tale. Now, I want to throw in here a little perspective from reproducibility issues in general and what Ioannidis calls meta-science or science about science. If you think about his famous paper, Why Most Published Results Are False, remember that one of the things that he proposes is the more people the more groups who are working on some problem, the more likely you are for somebody to get a positive result on the whole thing. And this is clearly the problem, and the case and the problem in the natural language processing world, where we have things that are in vogue and all of a sudden everybody's doing the same thing. Well, Salzberg and Ioannidis would both posit that just by virtue of the fact you have more people trying, the probability of somebody finding something a positive result goes up. And like Salzberg says, the people who got the negative results don't bother to submit it because our field is very biased towards positive results. And the picture of the technology or the science in the literature is really different from what it is in real life. Back to the paper. In other communities, for example, testing new drugs, experimenters tried to deal with this phenomenon of quote unquote community experiments by duplicating results. Proper duplication requires drawing a new random sample from the population and repeating the study. However, this is not what happens with benchmark databases, which normally are static. Now, I want to interject here. In natural language processing and information retrieval, we often have very strong, almost religious beliefs in the idea that you should never change that data set. Even, for example, if there are errors in the annotations or in relevance judgments, if you want to be able to compare future experimental results with past experimental results, then you have to have that same data set. So it's not like this is a crazy idea, there's a rationale behind it, but it does introduce this issue with not having new populations. So I'm going to go back to this, the beginning of the paragraph. In other communities, for example, testing new drugs, experimenters tried to deal with this phenomenon of quote unquote community experiments by duplicating results. Proper duplication requires drawing a new random sample from the population and repeating the study. However, this is not what happens with benchmark databases, which normally are static. If someone wants to duplicate results, they can only rerun the algorithms with the same parameters on the same data, and of course, the results will be the same. Using a different partitioning of the data into training and test sets does not help. Duplication can only work if new data becomes available.